sampling from a pool of objects. So there's some probability distribution, pi, and I is basically sampled from this probability distribution with probability pi. It's a rather strong assumption. You might say we can actually relax this a little bit and let these pi's change over time, but the assumption of independence is actually rather important for us. Okay? All right. So this is reasonable from our perspective, because if you look at internet traffic, if you look at this one cache that all of the CMU people share, usually there's thousands or millions of people that use the same cache. So basically, if your request stream has some correlations, some interdependencies, because you always go to CNN and then to BBC, if you look at the aggregate of all these different people, basically we have an approximately independent result. This is obviously not fully true in practice, obviously, but this is an approximation. And for this reason, we'll basically verify this empirically. We have all kinds of traces that are actually true from practice, where we basically not necessarily meet this assumption, but we are still doing well. We'll see that towards the end of the talk. The second thing I want to point out here is that you might say, given that these are just sampled from this distribution, just looking at the trace, I might be able to reconstruct the distribution and then just statically store the most popular objects, right? I mean, that seems like a reasonable heuristic. So we call this static caching, and you might think that might be optimal, but it turns out it is really not. Because we are looking at offline optimal caching, where we actually get to see the realization. And it turns out there's a simple example where the actual offline optimal policy is at least 50% better than the static, the caching of the statically most popular objects.
What does it mean? I mean, like when you, it's like one outcome of like a draw, whereas the offline is much better than the statically cached version?
I would say if you have a long enough trace, every outcome. I'm happy to talk about this a little bit more. We just need a little bit more notation. Okay. Okay? I'm hoping when we go there, we can make that a little bit clearer. I just wanted to point out that it's not trivial under this assumption. So this is the main cause here.
But like almost all outcomes when you have like a very long trace, like the trace is going to
I would say almost all, yes.
And also the trace length is going to infinity or something?
You have to assume that you have the trace length has to go to infinity. So this is actually the second assumption. The second assumption is that we look at an asymptotic regime. So if you look at the number of requests in the trace and the number of objects in the trace, and also the cache size, all of that we have to let jointly go to infinity. So when I say the cache size goes to infinity, we will actually not just set it to infinity, it's still kind of a fraction of how many objects you could put into the cache. So we scale the cache size such that the hit ratio stays the same. So it's still a small cache size, but all of these go to infinity. And why do we assume this? Because in practice, A, caches are rather large compared to the object sizes, and second, N and M, what we observe in practice, are in the tens of millions, hundreds of millions, or even we're starting to look at billions of requests in a trace. So this is why kind of this asymptotic regime actually even applies in practice. So I think this is a very reasonable assumption. That assumption might occur in some cases, the independence, and maybe not in others. More questions about our assumptions so far? Okay, good. So what can we actually prove under these assumptions? So the first thing that we do is that we look at the LP relaxation of offline caching, and we show that you can capture this problem as a min-cost flow instance. So that's actually very nice. A, it allows us to solve this LP problem much, much faster. And B, it really exposes a lot of the underlying structure of the problem, which we'll basically then exploit in our proof. And so based on this min-cost flow representation, we come up with the following result where under this assumption of stochastic independence, the fraction of non-integer decision variables goes to 0 as m goes to infinity in this asymptotic regime of assumption 2. The implication of this is if we basically get a min-cost flow solution for a given m, and this is going to reach a lower hit-miss ratio than the optimal solution because it could have non-integer decision variables. This is basically a lower bound, and then we also get an upper bound by looking at the min-cost flow solution and basically counting all the fractional misses as full misses. And under this theorem, the fraction of basically the fraction misses as n goes to infinity, this goes to 0. And so basically, we get an asymptotically exact result. Yes?
Usually when you use a flow model,
Yes?
you get integrality automatically.
OK. We do not have integrality because we have fractional costs. We have non-integer costs. And the integrality of Minkow's flow only applies if all the parameters are integer. Good observation, but unfortunately, it doesn't apply for us. OK? More questions about the results? Yes?
Do you get that the cost of the optimal, the optimal cost is like concentrated?
I'm not sure I understood that.
I mean, is it the case that like for a given set of PIs, you can just say like with high probability the optimal cost will be asymptotic to some deterministic function of PIs?
I'm still not sure I understood that.
The only input to your problem is those PIs, right?
Right, maybe n, I guess, if you...
Yeah, n and the p's.
I guess there's the cache size.
So it should be a...
But like
Oh, I see what you mean. OK.
The optimal
Oh, OK.
variable, right? Is it concentrated around its mean?
So what turns out to be the case is that since we look at the offline optimum, we assume that the trace was generated under our assumptions, but we actually get to see the realization. Right? If one object that is very popular doesn't end up being requested, we would still basically cache all the others in between.
Right, but it will be with high probability, right?
Well, this is basically the question if you go back to the static caching. Is the static caching optimal? And it can be arbitrarily bad. So even if you cache these most popular objects, I'm not sure I really understood your question there, but just knowing the PIs is just not enough to come up with the optimal miss ratio.
Right.
Because we get to see the actual trace.
Sure, I can see that.
So, question for you. So, is the simple example where opt is at least 1.5 better than static, is it simple enough that you can tell us? Right?
I can tell you in about 5 minutes when I've gone over more notation. It's very simple.
Okay. Because I'm kind of missing similar.
Well,
OK, if you want, we can just jump ahead and do that right now, if you would prefer doing that.
If there's like,
OK.
I don't know, but if there's like two objects, right, and one occurs with 51% chance and one occurs with 49% chance.
Yeah.
You don't want to maybe just always cache the more popular one, right? Because if like the lower popular one comes in like 3 times in a row, which it will with high probability in a really long stream, then you'd rather have it stick around for a little bit.
Exactly. That's it.
Right.
Yeah.
But, okay, go on.
OK.
Other question, maybe a little later.
All right.
Wait, sorry. So I'm just a little bit unclear on how we're actually measuring the performance of this thing now that we're in this probabilistic regime. Like, is it like this expected miss ratio, or is it? It sounds like you're just assuming that your trace was generated by this distribution, and then you like have to just solve it for that one trace, and you just measure against the offline optimal of that one trace.
We do not want. I think in expectation, static caching would be optimal. If you don't really look at the realization, we actually look at the realization. On this trace, we will basically, we solve, our algorithm works on the actual trace. It does not work on the probabilities.
So how is the probability part used?
Yeah, that's what happened.
Because then I'll just have everything supported, and then
Okay.
comparing against any arbitrary outcome.
I guess you only have to consider like certain styles of traces.
Exactly, that's the point.
You don't have to worry about like terrible traces. You can assume
Exactly.
it's somewhat nice looking.
There's a set of NP-hard traces. We're not solving those.
But
We're solving the subset that are basically.
High probability your trace will be like nice enough that you can solve.
There's no
Exactly.
wrong statement if I'm looking at the
It's
outcome.
still possible that you'll get a really bad trace.
Yeah.
I know what I'm saying.
As long as the bad traces
but
are supported.
Yeah, but what I'm saying with like, I assume like you're gonna say something about opt like with, I don't know, some probability over the choice of input.
We're making a probabilistic statement. That statement is that basically the probability of having these fractional misses goes to 0. And as you have a really, really long trace, that probability actually comes into play, right? You're just like law of large numbers of some sort, right? It's a probabilistic statement. There is still a probability that even in an infinite trace, I don't think for an infinite trace this could be true. Okay, for any finite trace, it could be an adversarial sequence, even if it is a long one. Yes. We could do bad on those.
So
Okay.
you'll be close to optimal with some probability.
Well, they're just
Depending-
estimating.
depending on
They're just
the
estimating the optimum right now, right? They're saying with like good probability, this whatever the LP relaxation is will be close.
Yeah.
Like,
Okay, yeah. Let's maybe, I think this is just what I mean is we are speaking a slightly different language. I think we might need to take that offline and clear up our language. All right, let's move on a little bit. So this is what we want to prove. And basically compared to the best prior work under these assumptions, where the prior work gets a 4 approximation, we get basically an asymptotically exact result. And so in the following, we basically want to talk about the proof and kind of the proof steps here. And so the outline for today is that we will start with this optimal caching ILP as you have it in the literature. And we will transform this as a first step into a different ILP, which we call the interval ILP. Because actually relaxing that original representation leads to that bad bound that we already know about is bad. And because this problem kind of looks like a square grid, it looks like my bathroom floor. So I'm having here some funny pictures that just kind of represent how they look like. And the interval ILP looks like railway tracks. So basically we'll start with the bathroom floor and compare it and get on the railway from there. And then we will relax this interval ILP to an LP and then convert this into Minkow's flow. And the Minkow's flow instance looks like a river. So that's why I have a picture of a river here. It's just basically having downstream flow in one direction and a couple of branches off. And from there, from this Minkow's flow graph, we will come up with a precedence relation. And that precedence relation basically enforces certain decision variables to be integer. So this precedence relation really is kind of the key idea that later on allows us to bound how many non-integer solutions there will be. And then finally, we will translate this problem into the well-known coupon collector problem. And this is where some chocolate comes in and we could celebrate Christmas. Okay, so that was the idea for today, to kind of translate this into a problem where we know we won't be able to solve like all the probability that we need to solve this problem, but basically just the intuition of what the key problem behind all of that is. All right, so we'll start basically with this first step, then we do the second, the third, and the fourth step. Okay? All right, so in this first step, oh yeah, and then we'll have some empirical results just to show that this works in practice. So in this first step, we start with this classical ILP. And as I said before, it looks kind of like a grid. So we have these two-dimensional decision variables. We have xij, where basically the ith object, whether it is cached at time point j, basically is represented. So if you have 4 different objects, we have 4 rows. And at time 1, we basically, for every object, keep track of whether it's cached or not at time 2, and so on and so forth. Yes?
Sorry, when you said cache, is that put into the cache, or is it in the cache at this time?
So if you basically put object A into the cache all the way through here,
yeah,
you will have a cache hit here.
But so like all the variables are 1. It's not the time that you put it in is 1 and the rest are 0.
Yes. Okay. But you're already making a good observation here, because this is overkill. I mean, this is really storing too much information, and this is what makes kind of relaxing this not give us good bounds. So the first observation you could make is, since we have this no prefetching assumption, if you look at object D, it is the first time requested at time 4, we will never need these decision variables. So that is encoded as an explicit constraint in this ILP, but it just, you have all these decision variables basically there for nothing. And the second observation is, if you look at any interval, if you look at B to B, there's always an optimal solution that either caches an object for the whole interval or not. So if you assume there's an optimal solution that just caches the object B for part of the interval, but not the whole interval, it will get a miss. So you could just not cache it for that first half of the interval and also get a miss. So you could get the same miss ratio as basically as this problem by just always storing it for the full interval or not. So that was basically your observation from before. This is just overkill. So it's kind of an all or nothing property. You only need to make decisions for intervals of requests to the same object, for consecutive requests to the same object. And this basically is the interval ILP that we use. It's just a one-dimensional representation where we just ask, do we cache the ith interval? And so that basically looks like these railway tracks, where for object A, basically, for this whole period from when it is first requested until it is second requested, you make decision whether you cache it in here. And so basically, a good intuition here is that you can think about the height of this object as the size of the object, and basically this whole room here is how many resources it uses, and the cache capacity basically as a vertical constraint says how many bytes you can keep in the cache at any given time. Is that clear so far? Okay. The objective is to minimize the number of misses. You will have a miss whenever a decision variable is 0. Whenever this decision variable is 0, you will have a miss here. So basically minimize the number of decision variables that are 0.
The input for this is the trace or the probability?
The input is the actual trace. Yes. Okay. If you want, this is all the notation we need to answer that other question. I had that as a backup slide in the end, but if you want, we could jump to that. Basically, it is just as we had before. If you're given, so let's say A is a very popular object and you're given its interval, the question is how many unpopular intervals could you fit into that interval? And that basically gives you in the offline setting a higher hit ratio. Okay? All right. So once you have this interval ILP representation, well, this is an NP-hard problem. We have to relax it somehow. So we basically do the LP relaxation of that problem, right? And the question here, once you're now in this linear program, can we do better than just solving a linear program for this case? Can someone see some underlying structure in this problem? So as we mentioned before, yes, we can solve it better. There is a min-cost flow instance that basically equally captures this problem. And so in the next step, basically, we will just talk about that min-cost flow problem a little bit more. Okay, so in this second step, we will start with this interval linear program, and we will then just construct a min-cost flow instance. And so in order to construct that min-cost flow instance, I will use the following notation, where if you have two nodes, so there's an edge in between, I'll basically first annotate the capacity and then the cost. And I'm sure most of you know what min-cost flow is. Basically, you're given some surplus of flow and some demand for flow, and basically you can route each unit of flow through the network such that the minimum cost occurs. And each time you use an edge, basically you pay this cost here. I think you probably all know about that, so I won't need to explain that too much further. So I'll give you the full min-cost flow at once for this instance up there, and then I'll just go through it step by step. So this is how it looks. For every interval that we had originally, we will have a node in here. We have a full, basically, we have these inner edges, the black edges, which go through the middle of them, and then we have these outer edges. We have one outer edge for each interval, and basically routing flow through these outer edges means we will not cache the object. So they have some cost. I will explain that a little bit more. And these inner edges, they correspond to caching that object, caching the bytes of this object in the cache. So they have, if C is your cache capacity, they have basically upper capacity for these edges is C, and they have 0 cost. Because if you cache it in there, you basically get a cache hit. Question?
Sorry, yeah, I just want to make sure.
Okay.
Do you pay that cost if any flow is flowing, or is that the amount of cost you pay per unit of flow that flows through the edge?
Per unit of flow.
Okay.
Basically, our units are bytes per byte. And so we have an axis of flow wherever each object is requested first. And then min-cost flow basically has to make the decision, should the flow be routed through the outer edge, where we will pay 1 over the size of the object in cost, which means if all the bytes of this object will be routed here, we will pay cost 1. This is where another cost metric could come in. You could encode that here, just as a small comment. But we basically want to have 1 cost if the whole object is not being cached, and that basically means going through that outer edge. On the other hand, if you basically route all the bytes of this cache through the inner edges, you will basically require capacity along the whole interval of that object. And so for every object, we will have a surplus of flow whenever that object is first requested. And min-cost flow basically has to route that flow all through the network until a final node where we have demand for all the objects. Does that make sense? Do we have more questions about the min-cost flow instance? So we basically prove that this gives equivalent solutions for the interval LP. And as I said before, these inner edges basically enforce the capacity constraint, and these outer edges, they create the cost of cache misses. And basically, the decision variables that we had before, whether an object is cached or not, basically corresponds to 1 minus the fraction of this object size, basically how many bytes you will route through that outer edge, right? And that clearly also shows you could have fractional solutions, right? You have non-integer solutions if part of this, like half the bytes of this object go through the outer edge and half of it go through the inner edge.
That's really where you're getting.
This is where we're getting.
It is integral, but it's no good because your cache is either all or none.
You're right. I did not even explain that right before. You're right.
Yeah.
Good point. That is a good point. Yes. Okay. That explains that. Good.
If all the sizes are 1, then I guess would this now become integral? So do you recover like the original option?
Yes. If all the sizes are 1, we get integral solutions and we get the classical caching offline optimum. Although solving a Minkow's flow is probably, I think, less efficient than actually doing the greedy algorithm.
So the other algorithm does something very different.
It does something rather different from this, yes. Okay, all right, so this is basically the Minkow's flow representation that we use. And so now we've done step 1, basically going from my bathroom floor to the railway track, and step 2, going to the river. And now we just have to go queuing before we get any chocolate. Okay, all right. So the next question is, how can we bound how many fractional solutions there are? Okay, and as I said before, we want to introduce a precedence relation to do that. And so the precedence relation that we will use, I'll just give you an intuitive decision first, which is if we look at this, so this is just a cutout from the Minkow's flow instance we had before, where we have this outer arc here, which has cost 1/3, and this outer arc here, which has cost 1. And let's assume you basically want to route some flow, because you have some excess of flow here, you want to route some flow through this network here. And let's further assume basically there's no capacity left on these inner edges. Where would you route the flow? You would route it along the edges with the least cost, right? And because all of these basically point into the same direction, basically everything flows into the same direction, you would always prefer this outer AA edge over this outer BB edge until you hit the capacity limit. When you hit the capacity limit, you have an integer solution. Okay, so a little bit more formally, you can basically define this precedence relation for any 2 intervals, I, J, and KL. And basically, if you have any interval, I to J, it will take precedence over another interval if it is contained in this. So if you have basically, let me quickly draw this. If you have an interval like this from I to J, it will take precedence over another interval K to L if it could be contained in it. Which makes sense, right? Because this is clearly better than this. It has less volume, and it basically could just be exchanged without giving up any misses.
So it's just if the volume is bigger or it's contained?
It is actually strictly contained, yes.
And the volume is bigger?
And the volume, exactly.
But what about the cost, though? I thought you were going to use
the cost.
Just using unit costs.
Yes, we have the same cost for every object. Like having one miss over another miss doesn't bother us. They're the same misses.
The cost per byte differs.
So the
cost per byte differs.
The cost per byte might differ.
Vertical length of these.
Exactly. So this might be size 3, and this might be size 5, or something like this. So this fits very comfortably in that other interval.
One, then that would not fit.
Exactly. So for this reason, we basically have 3 properties in the definition of the precedence relation. A, basically that it's from the vertical, basically difference that it actually fits in there from the start and end of the interval. And the third property is that the object size is even smaller. So it's a rather strict precedence relation, as you might think. But it turns, oh yeah, one more question.
Can we update condition 3 to be less than or equal to instead of strictly less than?
So it turns out in the proof of making all of this work in the Minkow's flow, it is much, much easier to have a strictly. You could totally fix that. but the proof would be probably 4 times the length.
Really?
So right now the proof is trivial. With that, it would be a little bit more complicated. Intuitively, it does not need to, but we just prefer to, you know. Okay. All right. So if you look at longer and longer traces, it turns out you will get more and more of these precedence relations. So in this case, we have this A to A interval, and we have this object B basically and this object C, which is contained in it. Let's assume their sizes are smaller. So 2 takes precedence over 1 and 3 takes precedence over 1. And as you have more and more traces, you will have a large tree of all of these precedence relations. Okay? And then you can show basically if one interval, takes precedence over another interval, so if xi takes precedence over xk, then whenever xk becomes a fractional solution, becomes larger than 1, then xi has to be 1. Because it means if you start filling up this guy, and you can always basically transfer it into that guy, if you start filling up that guy, you must have filled up and used all the capacity of that one. Okay? So basically this lemma you can prove for Minkow's flow. It might not apply to all algorithms, but this in general applies to the Minkow's flow representation of this. And this means if 1 ever becomes a fractional solution, 2 and 3 have to be integer. If 4 ever becomes a fractional solution, 5, 6, 7 have to be integer. They have to be 1. So that's the simple precedence relation. And basically the question then just becomes how many decision variables in the solution are part of this precedence relation. So how many decision variables basically are forced to be integer. Okay? All right. So the next step then finally is to convert this problem of how many decision variables are part of an integer relation into a tractable problem that we can address under these probabilistic assumptions. And so our goal is to upper bound the probability that an interval does not take precedence over any other interval, basically in all the decision variables that are in the hit set that are in the cache, right? And kind of our approach is to connect this to the coupon collector problem. How many of you have heard about the coupon collector problem? Most of you. Okay, so I almost don't need to explain it. So the coupon collector problem is you just have an urn with a certain number of coupons in it, k coupons in it, and you're sampling from that urn, and you're sampling it from it with replacement, and you ask until what is the time until you have all the coupons collected. Traditionally, this problem assumes equal probability for all the coupons. Turns out we have this problem where it's not equal, and that makes our problem a little bit harder. Okay? And so to celebrate this coupon problem and to kind of try out this coupon problem, I brought some chocolate for you to sample. And as this is the last talk of the semester, you can sample some chocolate to try from all the different coupons today. So just pass this today, and we'll do some coupon collecting in practice. I hope you like some German chocolate. I'm German, so I brought some stuff from my country. Okay, good. So how could we possibly connect these two problems? They look rather different, don't they? Okay.
In the spirit of the talk, we can take large numbers of pieces, not just one. Right? Just kidding.
I'm hoping there will be some left. Okay, good. All right, so how could we possibly connect these two problems? And so I've drawn a little sketch in here to explain that a little bit more. So we're looking at a specific, so let's just for the moment look at a specific interval, so xi, this is this interval here. And we ask the question, basically when does the case happen that xi does not precedence over any other interval? And this is basically happens if you look at all the other objects that are currently in the cache. If all these other intervals stop before this interval is completed, then clearly this cannot be contained in any other interval, so it cannot take precedence over any other interval. And so all these objects here, which is basically how many objects are in the cache at this very moment, these are the coupons that we're trying to collect. And the time until all of these occur is basically the coupon collector time. So The objects in the cache, basically, if we have HI objects, this is the K from the coupon collector. And this time until all these objects are being requested next is the coupon collector time. That's not the full problem yet, because we have to compare this to the length of this interval. So the probability that we're caring about, we want to upper bound the probability that Li, the length of this interval, is larger than the coupon collector time. Because in this case, this interval cannot take precedence over any other interval. I will not go into the details about how you actually upper bound this probability. Takes some math, but it's basically just probability theory, and you just have to go carefully through all the equations and upper bound that. Okay, so this is the basic idea, and that basically leads to the theorem I presented in the beginning. You will basically show that this probability goes to zero as the number of objects increases. We have questions about the coupon collector problem.
A question about something else?
Please.
I'm a little confused about the parameters. So like there's many parameters, right? You have like a fixed distribution on object arrivals. Or sorry, I mean a probability that
an object is being
distribution over sizes. Is that right?
Yes.
Okay, and like how many? And you have the cache size.
Yes.
And you have like the time.
Okay.
Is that right?
So if you basically have this trace of basically all these like A, B, C, and so on, the length is, I call this N.
Right.
How many objects there are, A, B, C, basically this is M. And basically all their probabilities.
Right.
And then their sizes, right? So that's basically size A, size B, size C. So we have N, the probabilities, the sizes, and M.
So for the cache size.
And the cache size. Yes. I agree, there's tons of parameters.
And what is like, yeah, like what is the dependence on the parameters for like the running times and the...
Yes. Okay, the running time of our algorithm is basically solving a Minkow's flow with 2n nodes, 2n edges, sorry about that. 2n edges and n nodes. This is basically, we have to solve Minkow's flow, which turns out to be n log n squared. So basically this is the running time of solving it. I mean, this is like a typical Minkow's flow. I mean, a general Minkow's flow algorithm not optimized for our instances at all will basically have this running time. It is an open problem for us to come up with better Minkow's flow instances.
Okay.
Sorry.
Then you also prove that like in the limit as n goes to infinity, your algorithm solution is like close to the optimal solution.
Yes, because
like the rate at which that occurred depend on the other parameters, like the size.
it depends on M.
Depends on M.
I think it probably, yeah.
But like
yet another.
Like SA to SB is like 2 to the n. Like that doesn't matter, or it does matter.
That's not a problem we considered.
In other words,
I would totally think.
Fix all the s's and the p's, then let n go to infinity, or like.
Yes, we are fixing the s's. Okay, it's a little bit more complicated to define how these behave. Like if you want to be formally correct, like in our technical report as we write it down right now, you have to be rather careful how you define all of these. But in principle, think about it as they are fixed as we go to infinity. But since you're adding more and more objects, you have to be rather careful how this actually looks.
But do you also say that m is going to infinity, or it's not?
M is going to infinity. So everything's going to infinity, basically. The most important thing is that m goes to infinity, and all the bounds that where the probability goes down are in terms of m.
But how do they go to infinity together, m and n?
Is that like 0.1 times n, or like square root n, or log n, or?
We have not considered the relation between these two. I don't know that it matters. I think every object has to be.
At least as fast as n.
Yeah, at least as fast as n. I mean, the assumption is that every object has to be requested once. So if you're adding more and more objects, all of them should have non-zero probabilities. N should be such that every object is requested once. That's the assumption.
So somehow like n has to go to infinity after m?
I think so, yes.
Okay, so, well, okay. Maybe
Okay. As I said, we are not considering things probably from your perspective, so you will have to.
Like, I guess n has to be at least like the min pi times n, so that you'll get each one with an expectation.
Yeah, that may. Yeah, I think that's roughly. Yeah, at least O that factor.
Yeah.
Okay. All right. Good. Probably we have to take some of these questions online. Just to conclude the talk, so we've gone basically through all the proof and kind of all what we've done. Kind of the outstanding thing is that we have some empirical results. I know you guys are not so interested maybe in seeing numbers and graphs and all of that. We have a whole bunch of them. I just want to show you two, where we basically wanted to go back to the literature and compare basically the miss ratio of some of these techniques. But it turns out that only OFMA is really what we can compute in practice. If you look at LP rounding, solving an LP with n squared variables, I mean, it didn't finish in 24 hours even for a small trace. Like we actually at some point let it run for a month, but it's just not very, yeah. And the same thing for that low curvature technique. I mean, the paper doesn't even prove it's n cubed. They just say it's a polynomial algorithm, and they never state it. So n cubed is kind of my algorithm of it. I optimize it as much as possible, but it's just so slow. You can do it for a couple of hundreds of thousands of requests.
So what is n? What is n?
N is the trace length, is how many requests there are.
In your experiment.
N is we are given a trace by a company.
No. What
What is n? 400 million. We have a couple of different traces. 400 million is, I think, a good ballpark. All right. Okay. So.
These results aren't
Yes. Oh, okay. That's a good point. Okay. All right. I mean, I think our algorithm probably scales into the 20 million range right now. We have a few more algorithms that are faster. They're really heuristics, but I haven't talked about them here. That's why I was thinking about 400 million. These results are about for 10 million long traces. Okay, sorry about that. 10 million is basically what OFMA can compute in about 24 hours, roughly. So even though this is n squared and we have worse than n squared, we're actually significantly better even in scaling behavior than OFMA. Why that is an open problem. How to solve our Minkow's flow problems. I'm most happy to hear ideas about solving our Minkow's flow instances faster. But okay, so here are the results. So this is one trace. This is a content delivery network, basically many internet requests, basically intermixed. And the miss ratio basically goes down like this. Our two, like the upper and lower bounds, and basically you can't tell them apart at all. They're exact. They're like within 0.5% on like the whole range of parameters, versus OFMA is basically all the way up there. And on another trace where we know that our independence assumption does not hold because we've basically analyzed this trace, we're still doing really well. The error is still less than 1%. And OFMA, for some reason, it does a little bit better. But basically, these are some representative numbers of what we see in practice. So as I said, the error is very small. And these are traces with 10 million requests. And low curvature in LP, we couldn't compute even 1 million requests within 24 hours. And on 1 million requests, all of these results are rather trivial. I mean, everything is just 100% misses because the cache hasn't warmed up at this point. So you really have to look at large traces to get any meaningful numbers. Okay, so this is kind of the conclusion from all of this. And just kind of as a summary, under the assumptions of stochastic independence and this asymptotic regime, we basically improve the approximation factor from 4 to asymptotically exact. And we basically went through all these pretty pictures until we finally got our chocolate. And that was basically the story for today. And as I said before, the open question, and that's very interesting, I would be very interested in working on this, since we have this very specific Minkow's flow instance where all the flow basically goes in one direction. One would think you could solve that much faster. And our algorithm solves, I mean, it is faster than n cubed. So it is already, like even a network simplex algorithm is already working much faster than it's supposed to work. And so we're thinking basically we should be able to get almost a linear time, or at least an n log n algorithm for these instances. So that's an open question. If anyone has any ideas about that, I would be happy to hear them. But that's kind of the conclusion for today. Thanks, everyone. Thanks for coming. Oh, that's on time.
Yeah, we don't have a ton of time,
Yeah.
unfortunately, since we were going to start another TCS Plus talk almost immediately.
Right.
I think there are lots of questions asked throughout. If there are any burning questions, we can ask them now, or else pick everything offline.
What does FOO stand for?
FOO. Where did I even say it? Okay, FOO stands for Flow Offline Optimal. Flow Offline Optimal. Yeah. Did I even mention the name at some point? It's in the table. Oh yeah. It's some table. Yeah. Okay. Yeah. I think it's an in joke, really, like the foo variable.
About online algorithms, do you feel like this work has given you an intuition about better algorithms for practical data?
So these previous works that I pointed out before, all of these analyzed the offline optimal and used it to come up with an online algorithm. So maybe. I would think you could.
Well, there's the one big headline takeaway, which is that there's a lot of room for improvement.
Yes.
Much more than you think by using other heuristics.
Yes. Okay, I haven't gotten into more of the empirical results, but one big takeaway message that we got on our traces is that previous heuristics, basically offline heuristics, agree with existing online algorithms. But we can show there's much further room for improvement. So people should continue working in this field. Or at least, yeah, we should. Okay, thanks. And yeah, just come and ask me.